My name is Dr. Jim Peploski. I'm the Director of Freshman Chemistry here at Clarkson University. I teach introductory chemistry to many of your sons and daughters. And I want to welcome you to Clarkson University's Family Weekend. In particular, we're here to take a little bit of a whirlwind exploration of some interesting chemistry, some of which is taking place around us on any day. So when I talk to groups about chemistry, I always begin with a question. And the question is always, if we're here to talk chemistry, what is chemistry? Well, chemistry is a science, and it's a science that is the study of matter. Everything that occupies space, anything you can touch, is matter. So studying this benchtop is chemistry. That's not very interesting. Chemistry gets interesting when matter undergoes changes. Chemistry is the study of matter and the changes that it undergoes. We call those changes chemical reactions. So let's take a look at a simple chemical reaction. Notice I put on my safety glasses. Be careful, don't say helium. Helium is what you get in a balloon down at the card shop on Valentine's Day. If that were helium, what you would be giving to your sweetheart is a bomb. I don't know if that's the sentiment that you want to convey. Not helium gas, hydrogen gas. Hydrogen gas is a combustible gas. We call that type of reaction combustion. Now, I always bring a spare. The reaction with oxygen is called combustion. Here I have a spare just in case I screw up the first one. And believe me, I have. You know, if I reach up and accidentally burn through the thread, then my experiment goes floating up in the ceiling. So let's take a look at the combustion of hydrogen gas once again. Obviously, the second one was a lot louder, but what did I do in the second case? I included in the balloon both the hydrogen and the oxygen that are necessary for reaction. Chemistry is not just about studying reactions, it's about controlling reactions, making them behave the way we want them to behave. So, chemistry is the science of studying and controlling chemical reactions. All right. I do this show for numerous groups, including University Family Weekend, but whenever I talk to groups, I emphasize the understanding of the science. That this presentation is sometimes given the title Chemical Miracles, Magic, and Mayhem. Lots of mayhem. But what you need to realize is that everything that takes place up here is a product of an understanding of the science of the chemical reactions taking place. It's not the result of magic. There's no such thing as magic. Or is there? Now, I just caused a chemical reaction. What did I do to cause that reaction? I shook it, and what did shaking it do? It mixed something in. What did it mix in when I shook it? What's up here? Air. And what's contained in air? Oxygen. This is what's called an oxidation-reduction reaction that resulted in the formation of a pink color. But if you look carefully at what's going on, that pink color faded away. This is a reversible oxidation-reduction reaction. I much prefer the pink, so give it a shake, and we have the pink back again. We can go through several cycles of this reaction with oxygen as long as I supply more each time. And you can let that set there, and it will turn colorless. Then you can pass it around, give it a shake, and it will change color. I can do this with different dyes to get different colors. And I can even, if I'm tricky, get different colors in the same container depending on the amount of oxygen. So if you let those set, they'll turn colorless, give them a shape, and they will change back to being their colored form. A reversible oxidation reduction reaction. Now, the first experiment that I did with the balloon, there was energy given off in that process. That we talk in chemistry in my course about energy being liberated by a reaction. You felt that energy as a shock wave. That you felt that energy as heat in the room. I've got another reaction here. I would like you to figure out how the energy is given off in this case. Let's see how the energy is given off here. Just make sure that this is all good here. Make sure you set up. Oh my gosh, that's hard. How's the energy? Whoa, that's pretty dim. That's not good. We should get better than that. Not great. I think my peroxide is going bad. All right. Chemiluminescence, the generation of light through a chemical reaction, is one way in which energy can be given off. We can use different dyes to cause different color changes. And so the liberation of energy in the form of light, there's no heat generated here. We call this chemiluminescence. Where do you see chemiluminescent reactions taking place on a daily basis? Things like glow sticks. In nature, bioluminescence. Bioluminescence. Animals communicate through the generation of light. Inside these containers, we have a self-contained system that generates energy and releases it in the form of light. So, we have a couple of these here for you. If you like. Make sure you get them to the back row, guys. You know, we got some people sitting up there. So, throw some over here on the side. You gotta get them out there, you know. Just gotta make the back row. Oh, that one bounced off. All right. Chemiluminescence. Chemiluminescence is the chemical generation of light. As long as I've got you in the dark, though, let me ask a question. Here I've got a bottle, and it's got a solution in the bottle. I've got one simple question. What color is the solution in the bottle? Is it red? Or is it green? Well, like lots of things in life, it depends on how you look at it. It depends on how you look at it. When I see the light passing through the solution, I see all the colors that are unaffected by the chemicals. I see the red. When I look at it at an angle, I see the colors which are being given back to me in a process called fluorescence, like a fluorescent light bulb and a glow-in-the-dark, or a fluorescent poster. We see the green color. And so, depending on the direction that you look at it, you see different colors. The interaction of light with matter is something which is fundamental to chemistry. So, let's talk a little bit. I'll pass it around in a second. Let's talk a little bit about light and matter. My students, we've just finished discussing the role that electromagnetic radiation, light, plays with chemistry. On the board up here, I actually have a sheet of material, phosphorescent material, glow in the dark. Now, everyone who's had a glow in the dark object knows it has to be charged up by putting it in the light. But not all light is capable of exciting the phosphorescent material. If I take a red light, a red laser pointer, and shine it on my phosphorescent sheet, the red light, the red photons don't carry enough energy to excite the phosphorescent material. Same is true for green. If I take a green laser pointer, and shine it on my phosphorescent sheet, nothing happens. Nothing happens. The green doesn't carry enough energy. But if I take a blue blue laser pointer. Only the blue light carries enough energy to excite the phosphorescent sheet. So when you put your material out in the light to be charged up, it's only the blue wavelengths of light that are actually charging the phosphorescent sheet. So we can write with light in our phosphorescence. All right, now we turn on the lights here for a second. All right, so let's see what we got here. I got a couple of these green bottles if you want to pass them around with lights just to see what hit a couple, there we go. So I'm just going to pass these around, let you take a look at these with the lights if you want. Check out the different directions of light. All right, so time to do some chemistry. Not all chemistry involves explosions, so let's do something that may be a little closer to home. Let's talk about some chemistry taking place in solution. Everyone here has made solutions at some point in their life. Most of the time we use water to make our solutions. When you were a kid, I'm sure you made Kool-Aid. How do you make Kool-Aid? You would take, a pot of water and add in a flavor packet, then dump in some sugar. And I'm sure as a child, you thought to yourself, gee, if 1 cup of sugar is good, then 2 cups of sugar should be better. What happens when you try to add that 2nd cup of sugar to your quart of Kool-Aid? It sits there on the bottom. It won't dissolve. We call that a saturated solution. I've got a couple of solutions here. These are super saturated. I have convinced the liquid to dissolve more of the solid than it should be able to. The chemical is called sodium acetate. Now, we can illustrate just how much solid is dissolved in how little liquid by taking a tiny crystal. I'm going to take 1 crystal of sodium acetate here and put it down on the table. Now I'm going to pour this material out. It may take a little bit, but bear with me. If I pour this stuff out carefully, you can see there is so much solid dissolved in so little liquid that when it does crystallize out, the water actually ends up trapped inside the solid structure. Now, unfortunately, I can't really pour and talk at the same time. But we'll see how high we can go. All right, well, I think we're going to quit while we're ahead. Let's see how high we can go. Holy cow, I never made one this tall. I'm going to quit so I look great. All right. Now, the thing is, it only takes one crystal to get this process started. 1 crystal of sodium acetate added to the liquid, and it starts to crystallize immediately. And then once it starts, there's nothing I can do to stop it. All of the solid material is going to crystallize out of solution as soon as I add that crystal. If you feel the bottom of this, feel the bottom. What's it feel like? It's not cold, it's warm. This process generates heat. Now, there's an everyday household item that you can buy that works on this same chemistry. Does anybody know what it is?
Hand warmers.
Hand warmers. Reusable hand warmers use a super saturated solution. To repeat this, all I'm going to do is take this downstairs, warm it up, put it on a hot plate, warm it up, and we'll go back into solution and stay there until the next time I crystallize it. And when I do, it'll give me some of that heat back, and I can warm my hands if I want. So reusable hand warmers work using a fairly exotic kind of a super saturated behavior of the salts. All right, you guys seem to like fire, so let's talk a little bit about, combustion once again. Here I have some phosphorus. Phosphorus is a combustible material. It will burn quite readily. I'll place a little phosphorus on this pedestal here. Now, in order to burn, what does the phosphorus need? What does combustion mean? It means reaction with oxygen. If I light this, you will see that it burns. It burns quite readily. But air is only 20% oxygen. Here I have a flask that is filled with oxygen. The combustion is dramatically different inside pure oxygen. We have the reaction of phosphorus and oxygen making P4O10. I call this the glowing orb of chemistry. The glowing orb. This is how I determine grades. I stare into the orb. Now, my students should recognize that I have a closed system with a fixed amount of oxygen and a fixed amount of phosphorus. This reaction can only proceed until one of the two materials is used up. We call it a limiting reagent system. So the reaction can only continue until one of the two starting materials is consumed, and then the reaction has to stop! There we go. Thank you. All right. The white material you see inside is the combined product of phosphorus and oxygen, P4O10. But one of those two starting materials is left over in there, depending on exactly what I started with. We call it a limiting reagent kind of system. What do I do next? All right, students and families and people ask me very, very frequently, Dr. Kim, what's your favorite demonstration? And I do lots of demos, these plus others in class. My favorite demonstration is by far the reaction of gases that have odd numbers of electrons. Odd numbers of electrons. Why is that? Well, we can check this out here. Fairly simple setup. I'm going to make a gas that has an odd number of electrons. It's called chlorine dioxide. I'm going to start with a little sodium chlorite. Place it in a test tube. And then I'm going to add some HCl. I'm going to add a little hydrochloric acid, and you should see, if you're way in the back, you may have to hold on a sec. You should see the formation of a yellow gas. I have to do this kind of slowly. We have a yellow gas forming. This yellow gas is chlorine dioxide. It contains an odd number of electrons. Now I'm going to add to that a tiny amount of sodium nitrite. How tiny? Well, like that tiny. Like the head of a pin. I'm going to add just the head of a pin worth. I'm going to add just the head of a pin worth. This wasn't quite right. Let's try this again. Head of a pin. There we go. Now, it's really kind of amazing that you can get that much of a reaction from a milligram worth of material. There are two chemicals that are generated in this reaction. Both of them have odd numbers of electrons. And one thing my students will learn in class, electrons like to be paired. So we have two things with each with an odd number. They want to get together, and they want to get together in a hurry. And so that reaction is one of the fastest known chemical reactions. It occurs almost instantaneously, and that tiny, tiny amount can cause, I'm going to have to ask you guys, unfortunately you can't be there. You can see the fire holes in the floor. So, that was just from last week, so you can't be on the floor right down here. Sorry. For your safety and mine. My legal safety.
Yeah, really.
All right. Let me see here. You guys seem to like, let me get this going right here. You like fire, you like combustion. So here I have a highly combustible material. This material is called lycopodium. Lycopodium. I'm going to place a little bit on this watch glass, and then I'm going to light it, just to prove to you that it is combustible. So, let me light the lycopodium. Something's wrong. In order to burn, what does the lycopodium need?
Oxygen.
Oxygen. As it lays there flat on this glass, it can't get the oxygen that it needs. So let's find a way to get it the oxygen that it needs. Here I have just a little set. This is just a little puffer assembly. I'm going to put the lycopodium in here. And now I need a flame. I could use just, a flame, but it's easier if I use a torch. The torch is just so I don't have to hold it. It could be a candle. It could be a candle. It makes no difference. All right, so now if I disperse the lycopodium in the air where it can get the oxygen that it needs, the combustion is dramatically different. It burns very rapidly. So all I have to do is disperse the lycopodium in the air, 3, 2, 1, and I get dramatic combustion. This can be a problem anywhere you have fine dust particles that can get in the air, like grain elevators or coal mines. You can have dust explosions that occur. Now I've been doing this demonstration for years with my students, talking to them about the hazards of fine particles and the kinetics of combustion. But a couple of years ago at Christmas time, I got a gift. And the moment I got the gift, I knew exactly what it was destined for. A couple of years ago, I got a Nerf gun. Now, if all I need to combust the lycopodium is a puff of air, what better thing than a Nerf gun? I've attached a flame to the front, and I've got a little reservoir of lycopodium here. So, let's see what happens. Let's see what happens when we try the lycopodium combustion again. Light our flame. Looks like something out of a Schwarzenegger movie. All right, here we go. Lycopodium combustion in 3, 2, 1. Not bad, not bad. All right, the lycopodium all right. Let's see here. For this next one, I need a volunteer. A volunteer who's close, obviously, with a dollar bill. You have a dollar bill? Have you ever seen the magic show? You got your dollar bill ready. You've seen the show before. You're cheating. You can't have seen the show before. You got your dollar ready as well.
No, I just handed it.
You've never seen the show before.
I did.
You like explosions. Are you brave? Come on down. What's your name? All right. What's your name? Joey. All right, Joey. Been nice knowing you. All right, you've got a dollar bill, right? We're going to set this dollar bill right here. Here I have an explosive material called triacetone triperoxide. Hold this for a second. You want to just stand off to the side over there so everybody can see what's going on. I'm going to place a little of this triacetone triperoxide on this dollar bill. All right, there we go. We got triacetone triperoxide on the dollar bill. Now, you may think that your job is to light it. Oh, before we do that, what does he need? He needs safety goggles. Well, I happen to have the perfect pair of safety goggles to show you. Here we go. Pop those on. You gonna stay on? All right. Oh, now, you may think that your job is to light the triacetone triperoxide. It's not. Your job is to hold the triacetone triperoxide. Just hold this hand out flat. Put that right there on your hand. All right. So, now stand over here so everyone can see. Hold your hand out far enough. There we go. Perfect. Now, I will light the triacetone triperoxide. Now, you don't really want to lose the dollar bill, do you? You don't want to lose the dollar bill, you know. That's value. The kids, you know, I don't know. So, save the dollar bill. You know, I will light the triacetone triperoxide. Hold your hand flat and up, and we're going to light the triacetone triperoxide. Triperoxide burns rapidly, but it doesn't detonate unless you have a larger quantity or unless it were confined to some type of container. So it generates most of its energy upward and we get the fireball. All right, thank you very much, Joey. Consider it an admission fee. There you go. Yeah. Okay. Let me see. There are all kinds of neat, interesting chemistry that takes place around us every day. Here I have a remarkable material, a new space-age polymer. This is called sodium polyacrylate. It's not too dissimilar from the stuff that you find in baby diapers. Not that stuff, the stuff that they actually put in the diaper. Its function is to absorb liquid, absorb water. Well, let's see how good it is at its job. Here I have about 20 grams worth of sodium polyacrylate. It's just a dry powder. I'm going to add about 400 milliliters of water. And let's see what happens. Add my water to my sodium polyacrylate. And in a second, my water has been absorbed. And now I've got this really kind of interesting stuff. Touch that. What's it feel like? What's it feel like? It's cool, it's fluffy, it's soft, it's fake movie snow. It's fake snow. You don't think those guys in Hollywood go off into the snow every time that they want to film a winter scene. They make their own winter. Now, this material here can be dehydrated. I can dry it out and it will go back to its original size and then do the whole thing over again. So this sodium polyacrylate can be used to make fake movie snow, absorb liquids. All right, so there we go. Let me get some of this junk out of the way. All right. Now today is a special day in the hearts of chemists. Anybody know what today is? It's mole day. The mole is a measured unit in chemistry. It's equal to 6.02 times 10 to the 23rd molecules. So at 6:02 this morning, on 10/23 of the year, that's what we call mole day. Now, many people consider mole day to be the day of celebration for chemistry throughout the year, but that's not true. There's a day in the summer which is really a spectacle of chemistry. What day in the summer is the real celebration of chemistry? The 4th of July. What's going on in the 4th of July? Nothing but brilliant displays of chemical reactions up in the sky. in order to do these types of reactions, all I need is some type of energetic material. And the energetic material supplies energy to atoms. And as those atoms become excited, they give you light in a variety of different forms and colors. So here I have a little bit of polymer, nitrocellulose. I've mixed it with a little bit of magnesium, some iron, some aluminum, a little bit of gunpowder just for kick. If we excite those magnesium and aluminum and iron atoms, we can watch them as they give back light to us. This is just a little bit of a ethanol swab, so I can light it and drop it in there. So let's take a look at our 4th of July celebration in October. All right, now let's start again. The burning of the nitrocellulose excites the atoms. Those atoms give off light in the form of electromagnetic radiation, and we see the sparks and we see the color. All right, so when we're talking about